Okay, welcome everyone. Today we're really happy to have Hongyu give us a talk on entanglement entropies of equilibrated pure states and replica wormholes. Go ahead, Hong.
Okay, yeah. Thanks a lot for the invitation. Yeah, very happy to virtually come to Chicago again. I would be much happier if I come in person. Yeah, so I'm going to talk about some recent work based on with my student Shreya Vadham, and so this is something which appeared in August. So yeah, let's just consider you have in the normal situation when you have a, say, quantum many-body system in some far from equilibrium pure state, say just gas in the room, which the suppose at the beginning all the molecules of the gas, they are concentrated in one corner of the room, and then we know eventually they will spread out. Okay, so the system, you wait a little bit, and then the system will look like in thermal equilibrium, even though it's still a pure state. Okay. So it's actually very hard to tell from your typical measurement whether the system is a pure state or is actually just a density matrix. And this is also precisely the situation we face in the evaporation of a black hole. So when you look at the black hole from all aspects, say if you make measurement around the black hole, if you say measure Hawking radiation, etc., study correlation functions in the black hole geometry, and you find for all purposes it behaves like a thermal state. It behaves like a thermal system. And but we do believe that black hole actually, if it's formed from a pure state, and if gravity does not destroy information, should remain to be a pure state. So now the question is, how do you actually tell? Okay, how do we distinguish that? So Page has made a very important observation in 1990s. So he observed that if you look at, say, entanglement entropies, so here I'm writing down also the Renyi entropies. So N would be the, say, Renyi index. So N equal to 1, you should interpret as the von Neumann entropy, and higher 2, 3, etc. would be, say, the higher Renyi entropies. And A would be some subsystem, say, of your system. And so there's a very simple relation. If you are in the pure state, then this Sn for subsystem A, then it's the same as the entropy for and Renyi entropy for the complement, which I denote as A bar. Okay, and this relation is not satisfied, say, if you have a mixed state. Say if you are able to say measure such quantities, or maybe theoretically calculate such quantities, then you should be able to distinguish, say, whether a system is in a pure state or mixed state. And in particular, if you can do this for evaporating black hole, then you can tell whether gravity destroys information or not. But in general, it's very hard to compute such Renyi entropies or entanglement von Neumann entropies for a general system. A standard trick, there's a standard trick is that you assume you actually have a finite dimensional, say you have a system with a finite dimensional Hilbert space. And then you try to calculate the average of all pure states. So you calculate the, say, average of this Renyi entropy, say, of all pure states. And that's not, it's normally the situation in physics, when you do a random average, the problem becomes much simpler. Okay. And then, for example, in the regime, which is your Hilbert space is very large, and yeah, for example, so dA here means the dimension of the dimension of the Hilbert space for the subsystem A, and similarly for dA bar. So in the case, say, your dimension of Hilbert space is not, total dimension of Hilbert space is not, and the dA and dA bar are not very close to each other, and then you find this very simple formula. And so this over bar here means the average of all pure states. and just essentially given by the minimum between the what you would normally call the cross-grained entropy for the smaller subsystem. Okay, so the log dA, say for subsystem A, the log dA would be would be normally called cross-grained the entropy, the maximal cross-grained entropy.
Sorry, how are you characterizing the subsystem?
You just.
I mean, I think my ultimate question is, when you start averaging over all pure states,
Yeah.
Then how do I know that A and A bar themselves aren't correlated to what pure state you're considering?
Oh, the subsystem. The subsystem is defined at the degrees of freedom, right? Does not depend on the state you choose. Yeah, so this is not the subspace of the Hilbert space. This is a subsystem. So the full Hilbert space is the tensor product, say, of the Hilbert space for A and the Hilbert space for A bar. So suppose if you have 5 particles, then we say 2 particles is a subsystem and 3 particles is A bar. And of course, no matter what state you choose, this separation does not change.
That's fine if my Hilbert space is just a tensor product of single particle Hilbert spaces. But when we have a field theory, that, it's more a question of what modes are excited.
Sure.
But still, I can have one state which has the first, third, and fifth modes excited, and another one that has the second, fourth, and sixth. So I'm confused about how this partitioning is going to work.
Oh, so the partition depends on your specific system. So here I'm just assuming that the Hilbert space, your full Hilbert space, can be factorized, say, into say HA and HA bar, and so this is the input. I consider assume a system have such a factorized structure.
Okay.
Yeah. For example, if you have a spin system and any number of subset of spins will always is a subsystem. Yeah, so if you have a spin system, you automatically have a tensor product structure associated with any subset of spins.
Okay.
Yeah, good. So this trick is very powerful. And for example, Page used it to make the prediction for the Page curve for the black hole evaporation. And he said that if black hole behaves like an ordinary quantum mechanical system, then they should satisfy. And if the black hole states are typical, and then they may satisfy this relation. Okay. Say if you assume a typical state behaves just like average behavior, and then they should satisfy this relation. And of course, you may have heard recently, people have made much progress in verifying this Page curve using gravity calculations. And also this trick provides much intuition for what to expect actually for actual systems, which may not have a finite dimensional Hilbert. Yeah, say for field theory with infinite dimensional Hilbert space, or for other more general situations, even though this does not directly apply, but still give you some intuition, maybe what to expect. But still, this actually does not help with actual calculation. Okay, this trick. This is average result, and you have to make various assumptions to apply it to a real system. And also, this result does not. There's no analogous result if you have a finite temperature. So finite temperature is not clear how you would do the average over all the states. And say if you have an infinite Hilbert space, you cannot do the average, etc. So, so the goal of today is I will propose a method to calculate the entanglement entropies and the Renyi entropies, say of such an what we call equilibrated pure state. Okay, so this means that it's a pure state. But yeah, I will elaborate a little bit more. But heuristically, just this is a pure state, but behaves macroscopically like a thermal state. Okay. And then we need, without the need of doing any average or assumption of typicality, etc. So we will propose that this is actually a leading terms of approximation, which can in principle be improved on. And then, also this approximation will apply to finite temperature, infinite Hilbert space, and the field theory, etc. And we will see that the answer can be expressed solely in terms of properties of an equilibrium density operator, and independent of the details of initial states, but yet compatible with unitarity. Okay. And then you can also apply this method to gravity systems. And then this provides a way to obtain answers consistent with unitarity using Euclidean, say, gravity path integrals. And for example, as an illustration, we can use this to give a systematic derivation, say, of this replica wormholes recently introduced to address the unitarity of black hole evolution and to verify the page curve. And in particular, this prescription elucidates the mathematical origin and physical nature, say, of such replica wormholes, and say why they give results actually compatible with unitarity. Yeah, because from the existing discussion, somehow why replica wormholes somehow magically give you results which compatible with unitarity is actually not very clear. Also, then in the end, I will offer some discussions. So first, let me just describe my setup, what I mean by this equilibrated pure states. So let's imagine you start with a pure state psi 0, which say is far from equilibrium. And then you apply some unitary evolution. So we assume, so this is the input. So we assume that the system eventually thermalizes, okay? Thermalize or equilibrates. And by thermalize or equilibrate, we mean that macroscopically, the physics of these states can be well described by some equilibrium density operator, which I call rho e. Okay, so this rho e can be written as a partition function times some unnormalized density operator. You can also just use rho e. It just for some purposes slightly convenient to separate them. Anyway, so what we mean by macroscopically well described, we mean that this equilibrated pure state, say, just like the gas in the room, you can associate, say, thermodynamic quantity associated with them, say like free energy, entropy, etc. And those thermodynamic quantities, they satisfy the standard thermodynamic relations. And also, if you make local fuel body measurements, then you get the results just like in the thermal ensemble. Okay, so that's what we mean by equilibrated pure state. Anyway, so so this is the input. We assume such a state will eventually equilibrate. And of course, if you have some kind of integrable system which never equilibrates, and then our discussion will not apply. And below, I will also sometimes call this Z alpha, the partition function for this unnormalized density operator to be the effective dimension. And the alpha here is some equilibrium parameters such as temperature, chemical potential, etc. And and also can be some other parameters, other conserved numbers. So now let me give you some examples of this I alpha. So for example, if you have a finite dimensional Hilbert space, say D is the dimension of if you have a system with a finite dimensional Hilbert space, and suppose the system eventually equilibrates to infinite temperature, say this happens, say if you take a spin system and the initial state of the spin system have sufficiently high energy, and then essentially the equilibrated state is like an infinite temperature state. And in this case, you can just take the this equilibrate density operator to be the identity, and the Z, the effective dimension, would be just the dimension of your Hilbert space. Okay, so when I is the identity, just means you can access all states in your Hilbert space with the same probability. And another example is the macrocanonical ensemble, which now you have the concept of the energy. You may have the concept of energy conservation, and then for this infinite temperature, you don't have to assume energy conservation. Okay, so macrocanonical ensemble, you can see the energy or the energy eigenstate in some narrow band, and then the dimension of the space in that narrow band would be your effective dimension. And also you can consider the standard canonical ensemble with just I beta just given by expansion minus beta h, and and then the z beta just the standard partition function. You can also consider more general ones, say with chemical potential, with say if you have some a system with even for some integrable system which can say equilibrate to this generalized Gibbs ensemble, and then you can also use that. And this R alpha is an important notation which I will use repeatedly. So keep this notation in mind. And so this denotes the unnormalized the equilibrium density operator. So do you have any questions regarding the setup? Okay, good. Okay, so now let me talk about a little bit about the Renyi entropy. So I will define, actually, mostly consider what we would call the Renyi partition function, will be the exponential of the Renyi entropy. So this is defined by you first evolve your initial pure density operator using your evolution operator U, and then this is the density operator. This will be the density operator at time t, and then you take the partial trace in A bar, you get rho A, reduce density matrix for A, then you take nth power, okay, and then you take trace over A, and then this is what we call the Renyi partition function, and the logarithm will be the Renyi entropy. You can write this also in terms of the path integral. So remember, in path integral, each evolution operator corresponding to a path, say you integrate from 0 to t, okay? And then for this Renyi entropy, essentially you have two M paths because you have U and U dagger. And U essentially going forward in time, and U dagger going backward in time. Okay, so you essentially have two M pairs of U and U dagger, and N paths which are going forward time, and then paths going backward to time. And then rho zeros then provided the initial state for this path integral, and then this trace structure then may be considered as providing the final condition for this path integral. Okay, and the integrand of this path integral will be just the action for all these different paths. Say n of them going forward, and n of them going backwards. So this phi prime denotes the field which is going backwards, and they have a minus sign because of the U dagger. And so let me mention that this talk will be a little bit notation heavy. So if you have any questions regarding the notations, please make sure you ask. Good. Yeah. Also, this quantity will be this notation will be used repeatedly later. Just keep in mind that this is the Renyi partition function. Okay. Good. So before talking about the approximation, let me first, in our approximation, the permutation group will play a very key role. So now let me first give you some heuristic feeling, where does the permutation group come from in such a discussion, okay? So if you consider this path integral, so this is like 2n copies of the path integral of your original system with the integrand given by this. And then in this path integral, actually there's a very special subset of configurations. So these are the set of configurations which is the path, the configurations which going forward in time, and the configuration going back in time, they actually paired this way through the, so sigma is an element of the permutation group. So essentially you can just separate them into n pairs, and with one of the going forward to time configuration equal to the one the going back to time configuration. So within this subset of configurations, then you notice that the essentially your integrand of your path integral is identical. The exponential inside the expansion is identically 0. So for those passes, there's no, essentially the phase suppression come from the oscillation of the phase, which you normally have in your typical, say, such kind of integrals. So one might imagine, okay, say if you consider some long time limit, which each s and each s can be large, and then you would expect this this phase will fluctuate a lot. So the typical configurations will average to 0, and then would be only this subset of configurations will perhaps play a dominant role. Okay, and so also one thing to notice is that within this subset of configurations, their contribution is time independent, because all the time dependence come in the in this exponential. Okay, come in the exponential when you do the integration for the action. So if this exponential identically vanishes, and then they actually contribute to the time independent expressions. Also, this is intuitively what you may expect when you approach equilibrium, and then your answer should be time independent. And so this is another motivation, say, such configurations could play important role. Okay, and so this suggests the relevance of the permutation group. Okay, any questions on this?
Should I worry that these configurations are a set of measure 0 in the path integral?
Yeah, so there are some subset of configurations. Yeah, even if they're measure 0, but if they if everything else contributes, say, average to 0, then they will dominate. Yeah, certainly there is such a So we have to be careful about that. Certainly. Yeah.
Okay.
Good. So so now I'm going to talk about the approximation, and then as I already advertised, the permutation group will play a very important role in that approximation. So for this purpose, I will first rewrite this Renyi partition function slightly differently, say as a transition amplitude in this what I would call the replica space space-time. In this replica space, which you have 2n copies of your original system. 2n copies of the path integral of the original system. And it's already intuitively very clear from this picture. This is like a transition amplitude. So you have initial states given by specified by 0, 0, and then you have 2n path integrals, and then with the final states specified by the trace. How you do the trace. Okay, so you have initial state transition to the final state. But this can be written a little bit more explicitly by introducing, so this is like transition amplitude in the 2n copies of original Hilbert space, with the two entropies of the unitary operators. Okay. And yeah, so mathematically you can just write them as follows. And with the evolution operator, just u times u dagger to the power n. So this rho 0 and the eta and this initial state and the final state are just mathematical notations. Yeah, are states in these two entropies of your Hilbert space, and I will define them more precisely. Okay, and yeah, heuristically they just represent this initial state rho 0 and the final trace condition. Okay. Yeah. So to explain this notation a little bit more carefully, let me just first mention a mathematical fact. So if you say take any operator in your original system, say in your original Hilbert space, okay, I call the script H. To take any operator in your original theory, you can define a set of n factorial states. So this is a canonical definition in the sense that the as follows. Okay, so for each operator, you can define n factorial states, and this n factorial state associate with the elements of the permutation group. Okay, for each element of the permutation group, you can define a state like this, which belongs to the two entropies of your Hilbert space, as follows. And I will define these states by its overlap with the basis in these two entropies, your Hilbert space. Okay, so the basis I say I choose would be say I1 would be the basis for H, and then I1 prime bar to it will be the second copy, and etc. Okay, the second pair, the second copy in the first pair, and then the second pair, and then the nth pair, etc. So I prime bar, etc. No, sorry. And then this O sigma is defined just by using the matrix element of your original operator, and then the permute to the second indices. Okay, using the permutation group. Okay. Yeah, since this is you may not see this every day, so let me just give you a couple of seconds to stare at this formula. Okay, so this definition is canonical. Say for any operator with this matrix element, and then you have this unique definition. Okay. Now as an example for the identity operator, and then if you then I will, yeah, for identity operator, then I will just use sigma. Okay, I will suppress this O. O is the identity. I just suppress it. I just use the sigma. So for the identity operator, and then you can define n factorial states labeled by sigma, and then that just corresponding to the various product of this chronological data, and with again permutation of the second indices. So why this is useful? Because, for example, let's give you two examples. So let's consider first the E, which denotes the identity permutation, and another element eta, which denotes the following permutation. So I'm using the standard cycle notation. So this eta means a permutation n goes to n-1, and n-1 go to n-2, etc., and 2 go to 1, and 1 go to n. Okay, just the cyclic. Yeah, and this permutation only have one cycle. Okay, have one cycle with n elements. So now if I take the O associated with the identity element in the permutation and contract it with the states defined by the identity operator, and if for identity operator there's n factorial, and one of them is the identity permutation. Okay, so if I contract that, then I get just trace O to the power n. And if I take OE contracted with this eta, and then I get I get O to the power n, and then take the trace. Okay, so the nice thing regarding this, essentially this can be imagined as a mathematical trick to incorporate all these different trace structure. Okay, essentially just giving you it's a mathematical notation. It's an algebraic notation to rewrite all these kind of different contraction structure among your operators. Okay, among your operator. And now this is very clear. So this Renyi partition function is just given by, say you have U rho 0, U dagger, take trace A bar to the power n, etc. And then this trace structure then just encoded by these elements. So eta is for A, for the A subsystem, which you have nth power. And for A bar, you just have identity. Okay, you just have the trace. And then you evolve by this U and U dagger, and the rho 0, E is just the identity permutation state associated with your rho 0. Okay. Good. So anyway, so this is just some mathematical trick to rewrite your Renyi partition function in terms of a transition amplitude in this replica space. Okay, in this replica space. Any questions on this? Okay. So now we can move a little bit forward. Now let me just motivate the approximation I'm going to use. So as I mentioned earlier, a powerful trick to calculate such kind of Renyi entropies or entanglement entropies for finite dimensional Hilbert space is you just average over doing random Haar average of all pure states. Okay. And you get those famous, you get the famous answer which I mentioned earlier. But there's a very important observation that when you do such, say, this is equivalent. Say I do an average. So when you do the average, this over all pure states, then it's the same. You're just doing the average. When I use this language, just you are doing the average of all possible use, okay, of your evolution operator. Okay, just average of all possible use. But the important observation is that this average over this U dagger to the power n, okay, can actually get you a projector. Okay, so this is the operator in two entropies of your Hilbert space. And now if you average over all possible U doing the Haar random average, it turns out that the result is a projector. And this projector is the projector onto the subspace spanned by this subset of the states corresponding to the identity, this n factorial state corresponding to the identity. Okay. So that means the average of this Renyi partition function, you can essentially, instead of doing the average, you can just rewrite it as a projection into the subspace. Okay, it's like you, instead of doing the time evolution, just do a projection. Okay, just do a projection. And to project into this, to the subspace associated with identity. So now we want to interpret this result in the two following ways. So the first, now instead of treating this as an average, now we can actually think of this as approximation, okay? Because we can think of this as approximation. And somehow you approximate this evolution operator. Yeah, we elaborate a little bit more further in the next slides. Essentially, you can treat that instead this as average, but as actually a approximation, which you just project to this subset of states. And in particular, you can check. Yeah, for this particular example, you can check that the variance around the average is very small. The fact that the variance around this average is very small can be translated into that when you build it as an approximation, this is actually a very good approximation. Okay. And also another observation is that the identity operator, which this is the n factorial state corresponding to the identity operator. And this can be considered as the equilibrium density matrix, unnormalized equilibrium density matrix for all such pure states. Okay, so in this case, there's no energy conservation, etc. When you average all pure, so when you take a typical pure state, it will thermalize into just identity, thermalize into a final state, which can be well approximated by the identity operator. So here, the identity operator is your final equilibrium state. Okay, it's your equilibrium density matrix. So with these two observations, so now we are going to now apply this to a general equilibrated pure state situation. Okay. So remember, here we want to understand the properties of this, say, entanglement property of this equilibrated pure state, and this equilibrated pure state is described by some equilibrium density operator, this I alpha. Okay. So now here is our equilibrium approximation. Yeah, I will not be able to derive this approximation, even though I believe maybe eventually approximation, the derivation of such approximation is possible. And but here I'm just going to propose it. Yeah, take it as a proposal. So now let's consider the n factorial state. Associate this operator, equilibrium density operator. Yeah, this is equilibrium density operator for your original system. Let's look at this n factorial states associated with it in your 2n copies of your 2n copies in your replica space. And then you can write the projector into such a subspace. It turns out that those states are not orthogonal to each other, so there's actually a non-trivial metric within this subspace. And Z2 would be the normalization, describe the normalization of any such states. Anyway, those details are not important. You just say you can actually project into the subspace spanned by those n factorial states. And now a very important properties of such states, essentially by definition, because they're the equilibrium density operator, but you can just easily check by some simple combinatoric manipulations that this when you act your evolution operator on such a state and leave this state invariant. Yeah, the same with the conjugate, the Hermitian conjugate of this operator. Okay. Then that means that suppose let's decompose the identity into the projection to the subspace and the complement projections, and now we can then insert this identity into this full expression. Okay. So you can just insert this identity in these two places. And then you get two terms. One is corresponding you project to P, and one you project to Q. And actually there's no cross term. The reason there's no cross term because the U leave the P invariant. Okay. So essentially when you have a P term, and then the U, I see if it does not exist. And then because of orthogonality between P and Q, and then they just factorize. Okay. So now the proposal is that we can just keep the first term. Okay, the Q term we just neglect. Okay, we just drop the Q term. We just restrict to the subspace spanned by the n factorial states, say associated with the equilibrium density operator. Okay. So as I said, I will not derive this approximation, but we will see that this approximation is reasonable later on. So any questions?
So how does all of this compare to sort of standard methodology for computing Renyi entropies, where I just do a path integral and I start cutting and sewing the domain in which the path integral is being taken?
Right. Yeah. Good. So normally, if I give you say arbitrary initial state, let me just go back to here. So if I give you an arbitrary initial state, give you some general non-equilibrium initial state psi 0, and then in general you don't know how to do that cast and pasting, because normally that procedure only applies to very special kind of state, say the vacuum, which you can write it as Euclidean path integral, or the thermal states, which again you can write as Euclidean path integral, and then you can do what you said. But for general states, even though we know it will, for general state we just don't have such kind of formalism. You can do that. And so what we are doing right now is I want to essentially reduce this problem, say doing this for general states into something you can calculate. Yeah. Does this answer your question?
Yeah, I think so.
Yeah, good. Okay.
I have another question.
Yeah.
So one way you motivated this approximation was that the variance of UU dagger to the n is small. If you do this, this is small. What is suppressing it? It's the dimension of the Hilbert space.
Oh, that's right. That's right. Yeah, a dimension of the Hilbert space. Yeah.
Okay, thank you.
Good. So yeah. So when the so you can actually simplify. Yeah, you can essentially just insert this project here, and then you get then we just keep the first term, and then you can do a little bit further. You can do a little bit further manipulation. I will not do it here, but you can show that when the system is notch, and for pure initial states, and then that expression can be simplified into expression which is actually independent of the initial states. And you just involve in this I alpha. So I alpha is just your equilibrium density operator. And yeah, overlap with this thing. Okay, so now it's expressed solely in terms of equilibrium density operator and independent of the initial state. So you find all your trace of the initial state has dropped out in this approximation. Okay. And so the key here, okay, so the key here is you actually sum of all permutation here. Say if I consider, say in the normal situation, yeah, let me just emphasize this point of sum of all permutations. Say if we say some initial state eventually thermalize, and then your first instinct to calculate, say the Renyi entropy or the entanglement entropy of these states after it has thermalized, you say, oh, let's just use the approximation just to replace it by the thermal density operator, and then just calculate the say the Renyi entropy using the thermal density operator. Okay, using that as a first approximation, and that would corresponding to, in this language, corresponding to you just keep the tau equal to identity here. Okay, just keep the tau equal to identity here. And that would be the approximation you would normally do. Okay, just yeah, just like you treat the black hole as a thermal state, you use thermal density matrix to calculate its entropies. And we know that way you just replace it by the thermal density operators and by the entropy of the standard thermal density operator, and that answer is not does not preserve unitarity. Yeah, as I mentioned earlier, because that unitarity constraint are not satisfied by such kind of by general density operator. So as we will see, the remarkable thing of this expression is that this is now expressed solely in terms of your equilibrium density operator, but actually it's compatible with unitarity. Okay, it's actually compatible with unitarity.
I'm confused by that. So you started off with something which was manifestly unitary, and then you split your trace into P and Q,
yeah,
and then you threw away Q. So didn't you throw away unitarity when you threw away Q?
Yeah. So that's naively you say, oh, how can you make? Naively you say, indeed, this should somehow destroy the unitarity, but as I will show, mention later, you can actually show this this expression actually by itself satisfy the unitarity constraints. Yeah, this is the unitarity constraint for the Renyi entropy, etc. Yeah, so that's the remarkable aspect of this approximation.
So this is again up to terms in 1 over the size of the Hilbert space?
That's right. Okay. Yeah. Good. Yeah. So let me just explain. So here I mentioned that when you I mentioned when you have a finite Hilbert space. When you have let me just say this again. When you have a finite dimensional Hilbert space, and now you can just rephrase the average. The average is corresponding to take the P. When you take the average here, essentially the Q just average to 0. You just get the P left. So that's the exact expression. Okay. So now we but here we reinterpret it as you for a single system, but you just drop the Q. Okay. And then you can estimate the size of Q by calculating the variance, okay, around the average. So if the variance around the average is very small, and then that gives you a very good estimate that for individual realization that this Q contribution is small. Okay. In the case which you can relate this to the average, then that would be the would be the justification for this approximation. But in the general case, as we said, if you have a finite temperature, or if you have a field theory, you have infinite dimensional Hilbert space, etc., then there's no such average you can do. Okay, but here you can still do a self-consistent approximation. Okay, so now let's imagine you calculate the part which you drop, which I call this Z and Q's, and then you square it. For this particular quantity is real, so we just need to square it. And now we apply this equivalent approximation to this quantity. Okay, so let me call this delta square. And then through some multiplication, you can also write it, apply equivalent approximation to this thing square, can also be written as essentially the difference between you first do the equivalent approximation to the square of the original full expression, and then first do the approximation and the square. Okay, and so the estimate that this self-consistent estimate of this thing is small, then would corresponding to the delta should be much smaller than the P part you keep. Okay, and so equivalently this just the delta is much smaller than this one is also approximate also means that this approximation can be factorized. Okay, whether you apply to the Z square first, you square first and then apply approximation, or you apply the approximation first and square, and these two are the same to leading order. Again, this leading order is in the large the effective dimension. Okay. So then indeed you can find, so you can actually calculate this explicitly. Okay, you can just apply this, and then you find that the self-consistent estimate of the part you drop with the part you keep is actually given by the square root of your partition function, of your equivalent partition function. So Z1 is your equivalent partition function. So if your partition function, as I mentioned earlier, you can interpret the equivalent partition function as the effective dimension. And so if the equivalent partition function is very big, and then this approximation is good. Okay. And so let me, this is a side remark may mention later. Anyway, so now let me just describe some general features of this approximation. And then here you can separate into n factorial terms, and each term corresponding to a permutation element, okay, say associated with your equivalent density operator. And now you can check this actually satisfies the unitarity constraint just because of the, just by but it's only unitarity when you sum over the permutations. Okay. So this is the way somehow you can approximate your state by the equivalent density operator, but still maintain unitarity. Okay, maintain the manifest unitarity. And also within this sum, there's two particularly simple contributions. So one contribution, of course, is just associated with identity, which I mentioned earlier. Then that's just corresponding to, you calculate the corresponding Renyi partition functions using the equilibrium density operator. Okay, this is just you naively approximate your pure state by the equilibrium density operator. And then another term corresponding to this eta. Remember, the eta is that the cyclical permutation, which is n go to n minus 1, minus 1 go to n minus 2, etc. So for this permutation, then you find that this corresponding to, you replace, you equate, this is just given by the Renyi partition function of the A bar when you replace the your density operator by the equilibrium density operator. So this is like the equilibrium Renyi partition function for the complement of the system, okay, for the A bar. And then for other element of the permutation group, the expression is more complicated. You cannot write it in this simple form. Okay. And now when one of A or A bar is much smaller than the other, then you can show actually then this just given by the minimum of these two. Okay. So and this recovers the standard result for the this page result during the Lupkin and the page and the Sasnoid result for the when you do the random average for the finite dimensional Hilbert space. But now this is a general expression. Also for finite temperature, also for field theory. Say if one of A or A bar is much smaller than the other, and then you find either E or eta dominates. So when A is much smaller than A bar, then you find that only the E dominates. Then you get that. And then when the A bar is much smaller than A, then you find that eta dominates, and then you get the equal to S and A bar. Anyway, you just get this expression. But in general, there may be other permutations to contribute.
Excuse me?
Yeah.
So how do I see that, like what's suppressing the other permutations here? Is there any way to see that when A or A bar is much smaller?
Yeah, I'm going to mention that a little bit. Yeah,
okay, thanks. Yeah,
just in the next slides. So the way you can try to estimate the size of each term is as follows. Okay, as I mentioned, so the way you can estimate the size of each term is as follows. So heuristically, what you can do is just count the number of traces. Yeah, remember as I said before, that what this kind of flotation does for you, this say permutations of tau and also this eta and E, what they do is they just give you different contractions of matrix element of I alpha. Okay, they just give you many different possible contractions, and then you can estimate the magnitude, say for each tau by counting how many traces you have. Okay, A traces and A bar traces. In the end, just relate. You get some number of A traces, some number of A bar traces when you do this contraction. Okay, when you do this matrix element. So it turns out the total number of A traces is just given by the number of cycles of tau, and let me denote that with k tau. And the number of A bar traces is just number of cycles of eta minus 1 times tau. Okay, and denoted by that. So now if we heuristically think that the trace A is proportional to some kind of effective dimensional Hilbert space for the A subsystem, and the trace A bar is some effective dimension Hilbert space for the A bar, yeah. If you have a finite dimensional Hilbert space, of course, this is just the dimension of the Hilbert space, but here we may also consider infinite dimensional Hilbert space, then dA and dA bar would be some effective dimensions. Okay. And now you can just and now with this thing, you can just estimate that each term here is essentially proportional to Ka to the power eta minus 1 tau and K bar K tau. Yeah, I might have, I think I might have written this opposite anyway. Yeah, anyway, just you get the powers of dA and dA bar and multiply with the power given by the number of cycles for those permutation elements. And then in particular, so so for example, and then you can just estimate, say if A is much larger, A is much smaller than A bar, then you just want to maximize this term. Okay, if A bar is much smaller than A, then you want to maximize this term. And when A and A bar are comparable, then you want to maximize their product. Okay. Also, a simple, just the combinatorial relation is that the number of cycles for tau and number of cycles for eta minus 1 times tau is actually always smaller than n plus 1. And when you saturate them, it's called the non-crossing partitions. Okay. So this is saturated by, we don't need to go into those details. They're saturated by certain subset called non-crossing partitions. So anyway, so if you want, when A and A bar is comparable, then you actually want to maximize the sum of these two, okay? And then you want to saturate this equality. Okay, you want to saturate this equality. Yeah, so this is just a general rule. You can try to estimate the size of each term and under different situations. So any questions on this? Good. You can also see this using some diagrammatically, using some visual. You can also see this visually using diagrammatically. Again, I will not go into details here. So you can actually, as I said, this is just some kind of contractions. So you can actually represent these contractions diagrammatically, and turns out you can write some kind of double line diagram to associate with this kind of contraction. The reason you have a double line because you have one line associated with a subsystem. For each I alpha, you have one line associated with a subsystem and another line associated with a bar subsystem. And so each I alpha then is represented by a double line. And then this contraction just this matrix element, this overlap just represented by some kind of contractions. And so this shaded thing just means each I alpha. And then the number of cycles, for example, here the system A is represented using the solid line, and A bar is using the dashed line. And then the cycle, then the trace for A and A bar then just corresponding to the closed loops, say, either solid line or the dashed lines, etc. So again, this way you can count the number of them. And then when you saturate this inequality, then corresponding to planar diagrams. So none of those contractions, they'll cross each other. And then you can also have long planar diagrams, etc. Okay. Good. So that's how you can estimate the size of each term.
Hong?
Yeah.
Hi, this is Paolo. Just a quick question.
Yeah.
At the transition point of the page curve, there is typically a contribution that goes like square root of the volume of the system.
Maybe ask you a question again. I will talk about some kind of transition regime in a little bit. Yeah.
Okay. Good.
For the finite dimensional Hilbert space case. Yeah. Okay. So the final remark is that, say, when the I alpha can be represented by the Euclidean path integrals, and now you can just represent this answer in terms of n replicas, then Euclidean path integrals for the n replicas of I alpha. So remember at the beginning, we actually have the Lorentzian problem have two n copies of your path integrals. But now when you reduce to this approximation, then this just can be reduced to the n Euclidean path integral for n replicas of I alpha, okay? And so essentially, this just reduced to a standard problem of doing the replicas of your equivalent density operator. But the difference is that now you have more, because now you have to sum over this permutation. So you have some exotic kind of contraction you have to include. So this tau equal to E would be your standard way to compute the Renyi entropy. So the figure A would be your standard way to compute the Renyi entropy for your equivalent density operator. But now if you want to calculate the pure state, then we are instructed you should also sum over other permutations. For example, when tau equal to eta, then this would be the contraction corresponding to you calculate the Renyi entropy for A bar. And then if you have other, and then other permutation corresponding to other more exotic contractions between A and A bar system. Okay. And so this just reduced to the problem of calculating the Lorentzian, essentially a Lorentzian question for calculating some kind of generic non-equivalent pure states, quantum information properties into those Euclidean part integral questions. Yeah, so this is now related to the question which maybe Paulo is asking. So now let's consider the regime which dA and the dA bar are comparable. So this will happen when you in the page curve, say if A is the black hole and A bar is the radiation. And then this will happen when you transition between the radiation dominates or the black hole dominates, etc. Yeah, so when A bar become comparable, and then you have to really consider sum of all planar diagrams. Okay, so the earlier then just not enough to include the E and eta, you have to sum of all possible planar diagrams. And then, then the general expression you can just write down. And this N, this capital N coefficient here, so this dA and dA bar power just follow from the number of cycles I mentioned earlier. And this N just corresponding to combinatorial factors associated with those non-crossing permutations. Okay, so you can write them down explicitly, and so this is for the transition region. Okay, so when one of them become much smaller than the other, then the first term or the last term dominates. But in the transition region, all of them dominates. Yeah, you have to sum all of them together. So Paulo, does it answer your question?
So I don't see how these, so I was referring to this correction, which scales like a square root of the volume. I wonder if that correction perhaps is included in the Q contribution.
Sorry, which square root volume correction you were referring to?
Right, so if I, let's see, if I write the von Neumann entropy just on the transition point of the page curve, I get, typically at least I get,
right, yeah.
Is this a square root of the specific heat?
Right, yeah, let me remember. I think that term is included in one of these terms here, yeah.
Let's see.
Yeah, included in here. Yeah, because of the, now you have to set them to be equal, etc. Yeah.
Okay.
I think it's included here.
I see.
Yeah.
Thanks.
Good. So now you can apply. So I'm already finishing my time. I have to speed up a little bit. So sorry, I'm going a little bit too slow. Yeah. So you can now also include apply this to the gravity system. And so now you can essentially just interpret this as the amplitude. Say even if you do in a, so this then can be interpreted as approximation. Say if you treat the gravity as a quantum system, and then you can just interpret this as some kind of amplitude in the full quantum gravitational theory. Okay. And if gravity respects the usual rules of quantum mechanics, then this prescription will lead to answer which consistent with unitarity. Even though you only needs to use the behavior of the equilibrium density, And so you may further implement, as I said, just this in this approximation itself. This thing should be interpreted as an exact, say, overlap, okay? But you may further approximate this, say, as using semi-classical approximation using Euclidean path integrals. So if you do this self-consistently, again, you will get a unitarity. You will get the answer compatible with unitarity, okay? And then for holographic systems, then the bound, then you guarantee to get the answer which is compatible with unitarity. Only, even though you're just using the semi-classical calculations. Okay. So for the holographic systems, then the boundary version of this prescription then provides the boundary conditions for formulating prescriptions for the Bach calculations. And so intuitively you get this kind of couplings among different replicas. then could lead to the replica wormholes. So those replica wormholes just corresponding to those exotic kind of permutation you have to include. Okay. And so yes. So this is approximation. So even if you calculate, you're able to calculate those overlap in the exact quantum gravity, still this is approximation. Okay, this is approximation, have nothing to do with semi-classical. So this is just approximation. Yeah, good. And so now let me just quickly discuss how this apply can be used to reproduce these replica wormholes people discussed recently. So let's just consider a situation where initial state psi 0 describe a star, and which under time evolution collapse to form a black hole and subsequently emit Hawking radiation. And then at some time t, describe upside and consisting of the black hole and emitted radiation. Okay. And then for simplicity, I will take this radiation subsystem to have a finite dimensional Hilbert space. Okay. And with no energy constraints. Okay. Yeah, so the HR is the radiation Hilbert subspace. Yeah, Hilbert space associated with the radiation subspace. And then in this case, then the equilibrium density operator to approximate this pure state, then you can just write as form, which you have an identity operator for the radiation subsystem, and then some kind of, say, thermal density operator associated with the black hole subspace. Okay. And so let's assume that the radiation subspace have dimension n, and and this black holes system will have some temperature, say inverse temperature beta. And then let's also assume that the black hole partition function, this thermal partition function for the black hole, they have such a big entropy factor. Okay, have a big entropy factor, and then some intensive, contributions. Anyway, so the regime, so one interesting regime to consider is both of them very large, but then the ratio of them to be finite. Okay, so that corresponding to the black hole and the radiation, they have comparable a number of effective degrees. They have comparable, say, effective dimension. And then you can just apply this. You can just take the formula. It's a very general formula. You can just immediately write down the general answer. And you don't need to really worry about the explicit form of this answer. So the key point is that then you follow Renyi entropy or Renyi partition functions, and then you can analytic integration to get von Neumann entropies. Then I just expressed in terms of the thermal partition functions of the black hole. Okay, so you only need to use the thermal partition functions of black hole. Just using the thermal density operator associated with the black hole raised to some power. Okay, and then you will get the unitarity invariant answer. So more specifically, let me just apply to this black hole model considered by this Pennington et al., the Stanford group. And there they consider some kind of the end of world brane black hole, which here this is the Euclidean configuration. This is the Renyi configuration. This is Euclidean configuration, and then you can write the equilibrium, the black hole equilibrium density operator for the black hole as this thermal part, and then a part corresponding to the end of world brane, which I just call it F. It can be some functions of H. HB just the Hamiltonian for the black hole part, for the black hole subsystem. Anyway, and so this function, the specific form of this function is not important. Just this some kind of additional structure corresponding to this the end of world brane. Those people introduce. And anyway, and then I mentioned here, entering into this Renyi partition function is those partition functions of your equilibrium density operator raised to some power, raised to some integer power. Okay, and then you can just calculate. Now given this prescription, and then you can just try to relate this to the gravity partition function, and then that give you this a replica wormhole, which they talk about. And this prescription tell you precisely what kind of replica wormhole you should include, and precise combinatorial factors, etc. Anyway, so you can do this for various cases. And so you list, and then you show that this actually precisely agrees with their results. Okay. And so physically, there's a very important message here, because there in their paper, they discuss that somehow this replica wormhole, could be, maybe it's a consequence, you have to do some average, etc. So here we show if this approximation is a good one, and then actually this replica wormhole can actually arise in the system with a fixed Hamiltonian. You don't need to do any average, and this is just leading term of some approximation. Okay, and in the paper we elaborate this point much more. Okay, yeah, here I will not have time to talk about it. Anyway, so this explains why, people sometimes have been saying that, oh, this kind of replica wormhole or this kind of island story seems like magic, which somehow Euclidean path integral, semi-classical gravity, how can that incorporate the unitarity, etc. So here we know why, because there's a very simple procedure, a simple approximation you can do. Actually, the answer is compatible with unitarity. Okay, so so this provides explanation why somehow just Euclidean semi-classical gravity actually can encode the answer compatible with unitarity. And so this also elucidates the underlying mathematical structure discussed in those gravity calculations. And you see that the key is the permutations. And in particular, for planar diagram, is this called the non-crossing permutations, etc. Yeah, you can also apply it to this example, which discussed by the other groups, which corresponding to the black hole, or internal black hole coupled to some flat space path. And again, you will get recover the same result. Again, corresponding to, you have to sum over some other configurations. Yeah. And you can also apply this to other examples. For example, you can consider, say, gravitational collapse in ADS from a pure state to form a big black hole. There's no evaporation. You can still ask what are the Renyi entropies for this big black hole, and then in order to get unitary invariant answer, and then this procedure tells you what kind of Bach manifold you need to sum over. Okay, when you sum over certain Bach manifold, and then that will lead to the unitarity invariant answer. Good. So now let me just quickly mention that here we underlying the dynamical assumption is that your evolution operator can take a far from equilibrium state to an equilibrium. Okay. And so normally people say such happens, say, to a chaotic system, non-integrable system. So certain integrable system can also equilibrate, etc. Yeah, so this is the input. Okay. And another important input is that we can ignore this contribution from this Q part. Okay, and then again, this you may consider as a property of U, such that somehow their contribution is not important. And so you might imagine, say, maybe for some integrable systems, this Q part can be important. Anyway, so now a natural question is whether this can be used as a general approximation for generic chaotic systems. Okay, so if yes, then actually can we actually derive this approximation, say, using some features of chaos or some features of the so then one in principle should actually derive this approximation. So here I'm just want to mention that one can show actually the equilibrium behavior of this Renyi entropy can actually be considered as a special case of a general dynamical properties of the operator growth. Yeah, because the Renyi entropies just involve the behavior of your initial Renyi initial density operator, and that operator have certain behavior, etc., and leads to the this behavior of the Renyi entropies. And and actually you can phrase it in the more general story. Just consider the operator growth of some generic operators, and then the behavior of the Renyi entropies then can be considered as a subset of that story. And yeah, so this is related to what we proposed earlier for the random void distribution related to the operator growth, etc. Okay, so yeah, so since I'm running very late, So let me just quickly summarize. Yeah, so it would be better, of course, to understand the properties of this ZAQ, and in particular the time scale. Yeah, we expect this should apply to sufficiently long time, but not too long time. Say should be long time enough that system actually equilibrates. But when you go to too long time scale, maybe then the fluctuation can become important, and then maybe the approximation will break down. Okay. And you can also apply it to correlation functions, and then yeah, for general correlation functions, as far as the correlation function all the time, you know, correlation functions are evaluated after system has equilibrated. Okay, and then you can approximate it using the equilibrium density operator. And then you can show that this approximation using our self-consistent this criterion to judge whether this approximation is good. Then you can show that the when all the O's are included, say if A is the smallest subsystem to include the product of all O's, and then this approximation is valid when A is much smaller than A bar. Yeah, so this is what we normally expect. And so now let me mention one situation this approximation does not work. Is that if you just consider, say, trace U and trace U dagger to the power n. So these have two n copies of U and U dagger. And in principle, you can apply our approximation. But here it's a little bit weird because there's no initial state, because you just try to trace over all states, and there's no equilibration here in this here too. Okay, so physically you would expect our approximation does not apply here. Indeed, and then you can rewrite. Yeah, you can try to apply our approximation. Then you can rewrite this as a transition amplitude in these two n copies, say, of the Hilbert space. And then you find that this is just corresponding to the trace of this evolution operator. And then again, you can just insert the projector separately in the ZP and ZQ. And now you find actually ZP and ZQ, ZQ is not surprised. And they become comparable. And so the approximation breaks down. Okay. And so people have been using this quantity to probe the, yeah, this sometimes called form factor. They use this to probe the discreteness of the energy levels. And in particular, people have been discussing how to calculate this on the gravity side. And again, some kind of replica wormhole, like kind of some kind of wormhole kind of configuration can be used to calculate this kind of quantity. But yeah, again, involving some kind of Euclidean wormhole or connecting different geometries of different boundaries. But now we see here in this situation, this kind of approximation actually breaks down. So that means, so even though the Euclidean wormhole here is very similar to the Euclidean wormhole which people discuss when calculating this page curve, etc. And yeah, gravity, at the gravity level, somehow they're similar, but here we see actually they have, yeah, but really in terms of a quantum system point of view, they actually have very different properties, and yeah, so actually they are physically very different from this kind of replica wormholes. Yeah, so I will stop here. Thank you.
All right, let's thank Hong for the nice talk. So maybe let's take one last quick question before moving on to the discussion.
Unless someone else has a question, in this equation ZP that plus ZQ that are both not suppressed, are they sign definite, or can they be anything?
You mean the ZQ?
Yeah.
Yeah, ZQ can be, yeah, ZQ certainly will depend on the time. So they're not necessarily sign definite, I'm not sure. But you can calculate, we have calculated in some very simple example, say, which you have, which you look at some stochastic Hamiltonian, then you can actually calculate some simple quantities, say for example, for n equal to 2 case, second Renyi entropy. And then you find that this dq actually have exponential, it decay exponentially. Indeed. So compatible with the but in general we don't know much about the dq. Yeah.
Okay. Thanks.
All right. Thanks, Hong.